Hi, everyone. Good evening, everybody here who is joining us for our webinar. My name is Bhavna Duggal, and I am here representing the SIUK team. First and foremost, thank you everybody who has joined us for a webinar today, which is on artificial intelligence in autonomous mobile robotics. Welcoming all the students, parents, and eminent professors who actually have taken out time and investing your time during this pandemic. So on that note, few of you may not know that what SIU is and perhaps what we do. So just quick introduction of SIUK. So SIUK is a global So in case you need extra information on our services, requesting everyone to visit our website, www.studyinuk.in. So on that note, now I would like to introduce our key speaker of the webinar today, Dr. Masuri from University of Birmingham. And she's a lecturer there of the School of Computer Science at the University of Birmingham. Her research is primarily related to knowledge, representation, and reasoning for robotics. She has focused on hybrid methods that integrate automated tasks and motion planning, scheduling, as well as temporal and spatial reasoning. So, Dr. Masuri, thank you so much for being here today. We are not able to thank you enough for having you here and helping students and professors. So, over to you now. Thank you.
Thank you. Thank you very much for having me, and thank you very much for the introduction. So my presentation today would be mostly about our intelligent robotic lab in the School of Computer Science, where I'm a lecturer in the School of Computer Science. And of course, I'm a member of Intelligent Robotic Labs. And within this description, of course, I'm going to talk about the research that each individual or as groups we are performing in our lab. And at the end, I would briefly explain about how our research is connected to our education, specifically our specialized master in robotics. So if I want to show one chart that represents what kind of research we are doing, it would be this. Basically, our research is centered around the intersection of artificial intelligence, machine learning, and robotics. And specifically, we are interested to combine methods from different field of study. Like, for example, if you consider control theory or automation, which is usually regarded as topics in robotics, or automated planning or multi-agent system, that's usually regarded as the topic from a classical AI method, or machine learning that speaks for itself. So we are interested to put these methods, when appropriate, together and make integrated intelligent system. I get more details. I will explain it in more details later, but before, so our lab is, we have 5 faculty, and I'm talking about our intelligent robotics lab, not the entire computer science department at the University of Birmingham. And we have 3 postdocs and more than 15 PhD students. And we are actively collaborating with the UK, EU, US, and New Zealand. And apart from the fact that the collaboration is really good, so because many of our colleagues, including myself, comes from different backgrounds. So I used to work in Sweden. Therefore, of course, I keep my collaboration in Sweden. And Also, many of my colleagues come from US, New Zealand, so we keep our collaboration alive, and therefore, as you see, we get many research funding from US, like DARPA, or from EU, Honda Research EU, Samsung's, and of course we are very active in getting funding, research funding from national EU, British funding like EPSRC. So we are pretty well located in terms of research in the EU, and also most importantly in the UK. And we are pretty much successful at attracting research funds, therefore employing many postdocs and PhD students. Of course, our members of labs are not just people. We have many robots. I did not put every pictures of the robots we have in the lab here. Actually, one of the pictures I put here is not we don't have it yet, but it's a kind of robots that we in our lab basically dealing with. It it includes basically mobile robots, different types of manipulation, dual arms, one arms, and drones, and kind of robot you use for educational purposes, like turtle bots. That and these are very important because when we teach, it's very important for us that students get the first-hand experience working with these robots, and they basically run experiment, getting an actual data, and each groups of a student, for example, if they are engaging, let's say, in the intelligent robotic module, so the one robot dedicated to each group, so they can actually make different tasks like navigation, mapping, localization. So it's pretty important also that the people get the first-hand experience. Therefore, we have enough facilities in our labs to help a student to get actual expertise in robotics. But I'm talking about robotic, and certainly the kind of robotics we are dealing with in a School of Computer Science is different from robotic, let's say, in engineering department. And we are really focusing on integrated AI system. Each individual picture you see in my slides is basically project in which we are basically not using an AI techniques, but rather many AI techniques. And many AI techniques in an integrated fashion drive the decisions and action each robot takes in these applications. And of course, this is just as examples of what we are doing. And I'm going through a couple of this application, not all of them. And in order to know exactly what kind of project we do, of course, you should go to our webpage and see the research project each of our colleagues is carrying out right now or in the past. But if I want to explain what the integrated AI system is and what our aims is I want to, let's say before getting to an example, what I mean by that, but I want to focus on what our general approach in our IRL lab. We are basically, as I said, we are working on integrated robotic system, and that sense and interact with surrounding. This can include collaboration with human. It could be multi-agent, many robots collaborating with each other. And many of our approaches we are using are inspired from cognition and controls in human and animals. And our focus area includes perception, computer vision, reasoning, learning, collaboration, and verification. It's pretty much everything. And this is very important because in order to make an intelligent robot, basically, you need each of this aspect to work together in an integrated fashion. So to basically have a realistic, real robotic example, if you don't want to make so many assumptions in in the AI solution you provide for an application, you really need to integrate this aspect. And that's basically why we have different expertise in our labs. And let's make one thing clear. What we mean by artificial intelligence is basically to build an computational artifacts to mimic human level decision making. Is not only learning about data. Artificial intelligence uh, is a field that includes both knowledge representation, planning, machine learning. So it's very unfortunate. And today, when people talk about artificial intelligence, basically what they mean, many of them, they mean machine learning. But artificial intelligence has a long history. And in fact, there are still many successful application of using other techniques than machine learning. But let's go and how we actually see how we combine these many approaches to make robot intelligent. A key component, as I said, is knowledge representation and reasoning, learning, control, and collaboration. We are really focused on explainable reasoning. What does that mean? For example, if we make a robot to enable to make a plan and does certain tasks autonomously, so the robot has to explain what has been wrong, why you come up to that particular plan. Of course, explainable AI at the moment is very famous when we are talking about machine learning and using black box techniques like a deep neural network, but explainable reasoning and explainable AI goes beyond that, and it's basically is a process of explaining or giving a description of why an autonomous agent come up to the particular decision and certain action. So this is particularly important when we're dealing with incomplete domain knowledge and uncertainty. And formal verification is also important when we want to, for example, employ robots and systems in industries. So we want to make sure, provide formal guarantees that, okay, our system does what we expect to do. So, and for doing that, we really need tools from formal verification to provide us with such guarantees. Of course, if you want to make a robot doing performing some autonomous actions, so the robot has to have basic understanding of what's going around. So this fall in part of the scene understanding, and in which we have a great expertise in our lab about scene understanding. And also we are working on manipulation and control. And also we are active in multi-robot and human-robot collaboration. I myself, my research is in knowledge representation and reasoning, and in particular hybrid reasoning. And an application I'm interested to study in robotics is actually multi-robot collaboration. So I'm happy to answer the details about the research within the multi-robot collaboration, multi-agent system, and knowledge representation and reasoning. But the rest, which of course I may not able to answer the details about the research as my colleague carrying out those. So, okay. I want to give you a brief story of a project started in 2012 and actually end of 2011, beginning of 2012, called RACE. And I was working in this project while I wasn't in Birmingham, but there's a reason I'm talking about this. And this gives us a motivation why we means by intelligent robotic system, why the kind of robotic we are working in our computer science department is different, for example, in engineering department. So in 2011, when we started this EU project, we were given this PR2 robot, and it was the first time after many years, and that the robot could do many things off the shelf. It could navigate, it could basically manipulate objects, and it could have basically percept object And all these things you can basically download some off-the-shelf ROS package and use an off-the-shelf method without the need of engineer specifying every details. So, okay, that we were happy that we have a robot does have basic functionality. All we have to do, we have to take some AI planning technique and let this robot set a table. And why I'm saying set a table, the use case of this project, it was a robot waiter, and among a lot of tasks, it has to be able to set a table. And we were particularly interested that this robot set a table without detailed instruction. All we wanted to give to the robot to do is basically, okay, this is the general description of the scene. What would this well-set table look like? And the robot, in order to robot do that, it has to perform kind of hybrid reasoning. It has to reason about where the object should go. At the same time, it should know that it has two arms. Basically, it can use one arm for holding things while moving the other arm around. And it has to reason about the time in which it wants to perform the action. So it has to reason about many different aspects to perform such a, I would say, competent task like setting a table. But we don't want to specify for the robot that, okay, the end effector position is this and that. So it's a high level description. And this high level description not only should work for this robot, it's PR2, it should, for example, for this robot, which is on one arm. It means that the robot has to have a high level understanding of, okay, now in order to move object around, it's not only enough, it needs to have some buffer zone, like a tray, to move things around. And this has to be integrated with different type of reasoning. Okay, how the object look like in the table, and what should I do next with respect to time and resources and the actions. So we are interested in the basically a general approach that we specify or kind of learning mechanism that can be generalized more than one set of tasks. And just before showing the learning part, so for example, this was a demo. We came up with this like in 2015, I guess. So you see that basically this robot doing the same thing. They both set a table. They confronted with a situation that is not a well-set table a situation. So they have to come up with a plan that change this object around. And probably this is not really impressive video that you see usually in the news of everything. But what is important that the description or high-level description is given to this robot is not a detailed description. It's basically a high-level rough plan, high-level description of what would be the action model look like, and what would be the well-set table look like. So now, yeah, you come up with the reasoning, you come up with a course of action that make a well-set table. Basically goes from the very high level of abstraction to very detail in the factor pose, but not but without specifying all those details. And this is the same for learning. So the previous task was about specification, but now here, so you see in these two videos, the robot does some polishing task, if the videos actually start. So I mute them. So they do pretty much the same thing. And you would wonder what is actually interesting in this video. But if you look closely, the surface they're polishing is different. And which means that the force that each robot arm they have to enforce in order to polish is different. So if you learn, for example, in this the particular task you're polishing a cupboard, so the force, so in order to change that to another surface, you have to learn a new set of force control. But we are interested to learn from a few examples that if we learn once, we can transfer the result to another new environment. And that is kind of things that our colleagues are really focusing on, that transform learning. And we basically generalize to the other tasks without changing the architecture. And this is the kind of intelligence we are looking in our lab. Kind of intelligence we are looking in our lab to enable the robots we are working with. Another application I would like to talk about is a drill planning problem. And this is really interesting application, at least for me. And I hope that I can explain in such a way that it makes you interested in it. It's a project that I was working while I was in Sweden. And it was with a mining company north of Sweden. And they were interested to make the whole drilling process autonomous. And this turns out to be extremely difficult problem. And why is the case? You see in the slides, this drilling machine is actually extremely huge machine. If I stand next to the wheels of this machine, it would be as tall as me. It was really intimidating even being next to that machine. So the problem is, given the field, this is a mining open pit mine, and the dot you see is a drill target. The robots or this drilling machine has to drill each point and in an optimized fashion, because we want to minimize the fuel, minimize the time that each robot is in the field, and for obvious reasons. But this till now, it doesn't sound really, really difficult. The problem is when this robot drill a hole, it creates an obstacle, and it creates a pile. Basically, drills the piles get around the hole, and that as an obstacle for the machine, because if the machine goes over those piles, the piles go back to the hole and defeat the whole purpose of drilling. So basically, it would be easily the case that the robot stuck in the middle of the piles it created by itself, or a robot with a stuck within the piles that created by other machine. So the order in which you drill the holes, it really affects the machine's motion. And this machine is not like us that can turn around everywhere we want. It's like a machine. It has a constraint movement. It cannot just move to the side. It has to maneuver like a car, and it's huge. And the spacing between these drill target are not that much. It's actually less than the size of the robot. So it makes this problem make it very difficult to solve. And the overall problem we want to solve is plan motion and drilling sequences for multiple machines such that the maker span is minimized. And the reason I put this particular application in this presentation, is actually we solved this problem, this specific problem, with basic AI technique, and we use a hybrid reasoning technique to combine reasoning about motions, reasoning about the time, about scheduling, and put these things together, and to come up with the solution, which I can show you a video of that. What you see in the video is a simulation, and the white arrow, if you can see, is basically the sequencing of the drill target, and the purple arrow is the approach angle. Each robot has to be where they are in each drilling target, and you see that the motion is animated with this polygon. And the important things you would notice later that this is the virtual fence, and the robot cannot go over this virtual fence because probably there is a rock or a cliff there. So in this particular example, there was a replanning case when the one robot is not anymore able to perform its task. So the robot on the top take over its job. But so there is something interesting happening here. You see the robot on the bottom then is not moving, and it's not by chance. The reason for that is this is the drilling target is supposed to be drilled by this robot. So if it would continue to drill, so this robot, which needs this space to maneuver, would basically destroy all those drilling. So this robot is waiting for the other robot to continue its maneuver in this confined space. And why this is confined space? Because of this virtual perimeter or here. So if when it's done with its all maneuvering, so it will continue to do drilling, and you will see in a second that's gonna happen. So it's a really crazy maneuver here. So I believe that if this is the last maneuver and the other one starts moving. Yes. And of course, there is a lot of details going on. And if you're interested to the details, there are papers, and of course, you can send me emails later if you're interested in these kind of things. So, but when we are dealing with robotic, in addition, we have to combine different sources of knowledge and different sources of reasoning. The uncertainty is a big deal. And then the important thing is how to reason about how to reason with different descriptions of knowledge, belief, and uncertainty, how to combine this uncertain information. And it is different because humans usually good with common sense knowledge and helps them deal with this uncertainty. For example, we think that books are typically in the library, but cookbooks probably in the kitchen. But robots often use quantitative estimate. Like I'm 90% sure that robotics books is in my office. So one of the approach that we are dealing with when we want to consider uncertainty in knowledge representation and reasoning, we basically reason about relevant information at different level of abstraction. And in particular, we use action language in different level of abstraction to deal with this uncertainty. So this is basically a pictures of my colleague Muhan actually work on this abstraction and intention. So imagine a robot has to go from office to the kitchen. So this is action language that describe this this movement in high level of abstraction, but is really different in which part of the room we are. The robot is, and which kind of action it has to take, and what happens if something goes wrong. So then you can basically discretize each room to a further section, and then if you want to deal with reasoning about moving in this room, so you have another action language that deal with the moving in that particular section. So you reason first, okay, I want to move from office to the kitchen. It's like me deciding to travel, for example, to India. I'm not thinking about the details, okay, which taxi I would get from here to the airport, but I just basically think about very high level, okay, which plane I get, and then I would decide about the details while I actually take the action. This is what happens, roughly speaking, here. So we have two videos. This is actually good examples of what kind of project a student could do. And the first one is actually about a robot making a high-level plan and perform it in actual environment to fetch a laptop. And basically, this is a high-level plan, and it shows that how the robot deals with the uncertainty in the environment, like the door is closed, so it has to wait till someone open the door. So the plan is not failed. It's basically the plan is still valid while the door is closed, and then if it's open, it assesses the situation and it continues to move. So And okay, I will skip the full video. Is basically what it does. It's basically fetch the laptop. So I'm gonna show you the other one. This is also interesting because, again, similar to the previous video, the robot make a high level plan, and to comply with the request that the user gives, and that is fetch, I think, the M&Ms. But when you will see in the video, when the robot perform this action, it's basically, instead of M&Ms, it's fetch something else, and that the plan will fail. And the interesting problem is, so how to use the plan you had and basically change the piece of it that went wrong, how to come up, how to diagnose what was wrong, and how to come up with a new plan with the minimal changes. And this is what this video would be about. It's actually a long video. So you see now is the RV simulation and the navigation actually in the map of the floor of the department. And okay, I will accelerate this. So it goes to the kitchen, and someone wrongly put, instead of M&Ms, put something else, and it finds its way all the way back to the person initially asked that request, and he realized that no, this is not chips. Oh, okay, actually the other way around. It's he asked chips. It wasn't M&M, so that was my mistake. So the things happened in the mind of the robot, which you would not see. Basically what you see is the redoing the action this time, but it's important which part of the plan it has to it has to execute, which part of the plan it has to maintain, and it needs high level reasoning for finding a successful course of action. Okay, so and this time, of course, surprise, is gonna give the chips to the, and the plan would be successful. It's actually very nice that the robot, it turns it around, and for the user to type what you want to type. For example, the goal is success. On all these details, it matters. Okay. So talking about uncertainty, I think this is my last slide about uncertainty. This is another project that I was doing in Sweden, and it was interesting how handling uncertainty is important. And also it was with the Volvo Construction Equipment, is a Swedish company. And this is a project also was a collaboration with the University of Oxford and the Volvo Construction Equipment and me myself, which is in Birmingham. Anyway, so the problem was multi-robot planning on uncertain travel time and safety constraint. So why this is the case? This is a map of a quarry. A quarry is a place that produce gravels. Basically, they crush the stones and to make the gravels. And they do this as you see in the crusher here. This is a cartoon picture, and there is another crusher here. We call it the primary crusher and secondary crusher. And these are the haulers. This is a small machine. They have to move around in this quarry to gather these crushed stones and dump it in the unloading area in somewhere here. And the problem is to gather as much as possible the stones, the gravel, and therefore to maximize the production. But this is not the entire story. The problem here is this primary crusher is always produce gravel, which means that there would be always a holder underneath of this primary crusher to gather this. And if there's no robot underneath of this primary crusher, these gravels would basically dumps in the ground and obstruct the path, obstruct the road of which robot has to pass, and the entire system would basically go to halt. So there would, should human comes and dig the gravel, and there would be huge financial burden if the process is halt, and in order to restart the entire process. So it's very important. The safety constraint here is one robot always has to be in the primary crusher. So you would think, oh, this is simple. You send all the robot to this primary crusher one after each other to make sure. But the whole process, the whole objective in this application is to produce, sorry, to gather as much as possible gravel. You don't want to create a long queue. It sometimes is good to send the robot to another crusher, but you don't want to really endanger the fact that no robot would be under the primary crusher. So how do you balance it? How to maximize the throughput at the same time respect this? So this means that you have to calculate precisely how long does it take for a robot to go, for example, to the charging station, to the primary crusher. If you calculate that, probably you can perform this assignment pretty optimally. But then again, the problem is a robot work in this environment, such an environment like this. Maybe there's a snow, there would be a slippery train, maybe there is a human pass by, so the robot has to slow down. There's a lot of uncertainty in the environment that the robot should take into account. So we cannot compute exact travel time. So that's planning under uncertain travel times comes to the place. And how we combine it with the safety constraint is a paper here, but it's basically we use approaches like a stochastic Petri net with combined MDP. We come up with this plan. The details is a macro decision project. The details in this paper, but this is the overall idea. I want to just explain the kind of problem we are dealing with and why reasoning about uncertainty is important. The last part in my presentation is about seeing understanding. So imagine this robot is a caregiver, and for example, it has to take an action in response to a particular state that a person, the caretaker, is. And in order to do that, it has to reason about many different things. For example, it has to know what kind of pose human is that person is eating, is sitting, is standing. In order to recognize activity, it has to reason about many different things. For example, the pose of the body. Does this person drinking, eating something? So it has to basically recognize what is in the hand of the person and where this person is looking. Is it has a full attention? So in order to understand the entire situation, you have to combine many different pieces, the pose, the hands, the gaze, and everything, in order to assess, in order to understand what kind of scene the robot is seeing, what kind of a state the human is, in order to take an appropriate action. So scene understanding is really important part of an intelligent robotic system. And we have an active group, we have an active computer vision research in our lab, in our department. So actually I put their awesome gaze estimation link to their GitHub. If you want to play with that, you can go, and the paper, one paper is here. And there's ROS package available. ROS is a robot operating system, for those of you who don't know. And Hyun Jin, my colleague, basically working in this aspect using deep neural network techniques. for eye gaze estimation and body estimation. Okay, and this is my last slide. And this is the part that I want to connect our research to our masters in robotics. So I explain about computer vision, about reasoning, about learning, and different applications we are dealing with. And these are the people they will teach in master, a robotic master. And these are the courses that are available for anyone who doing a master in robotics in a computer science department. And in particular, we have three module obligatory, like it's our core modules. That is advanced robotic, which I actually teach. It is about kinematic, dynamic, basic of robotic motion planning and control. We have intelligent robotic is about basically probabilistic robotic mapping, some simultaneous mapping and localization of slabs, reinforcement learning, anything deal with basic probabilistic robotic and the robotic vision, and basically the algorithm that are really important for nowadays computer vision. And of course, there's a whole amount of things that the computer science department can offer, and our student in robotic have access to that, like more specialized modular machine learning, data analysis, and a neural network, and similar and verification, and similar module. And I think that's my last slide. And here's the picture of the people I use their research briefly here. And I would like to put everyone's picture, like our PhD students and postdocs, but it was just too many pictures. So, and thank you for your attention. I'm really happy to answer your question regarding our lab.
Hello, can we move on with the question and answer session?
Oh, yes.
Yeah. So we have first question coming in, and the first question is how to get a chance for doing research in the lab.
Uh, okay, then I need more information, but because if it depends on what stage of in what stage of career you are in. For example, if you are a master student, then you should apply for a PhD study and carrying out research. If you have a PhD, so basically we announce if we have open postdoc position, and basically you have to follow the announcement of open position with respect to PhD, postdoc, lecturer, and basically different capacity that we employ people. So this pretty much it depends on the person who's asking.
Okay. So second question which we have is which language was used to design the basic intelligence of the robot?
Okay, you mean programming language, I assume.
Yes.
So okay, we usually use not all of us, but we usually use ROS operating system. And the good thing about ROS is it allows us to integrate different components, and it's most of the time the case that we don't use one particular language for designing all part of the system. For example, in the mining application, the motion planning was written in C++. The reasoning module is written with Java. So the perception part, and it was written in Python. So we use different component and wrap it in a Rust package and allow them to communicate to come up with a fully integrated system. Of course, if you are using a company software or company architecture, There would be another story. You have a constraint to deal with, to comply with those, but in research environment, we usually use ROS operating system, which doesn't have any constraint in the language you use. Therefore, people using different language, mostly people in computer vision, you're using Python. I use for reasoning using Java, or if I'm dealing with control, I use C++. So it's, I would say, pretty much everything.
Okay, thank you. The third question which we have is, does the robot has sensor on how many people are around and which other objects are around?
Uh, Robot has many sensor, but how many people are around and what object around are the
Yeah.
result of sensor processing. So the sensor, it doesn't tell how many, it doesn't tell this, what it sees is an object, is a person, is how many. These are really high level reasoning. Based on the sensory information you got, you should perform, and you should develop basically an algorithm to give in the sensor data. Sensor data, for example, in the case of Kinect, is RGB data, color with the dense. So it's a bunch of numbers. So you have to process this information and make sense of this information. And of course, the computer vision is about how to process this sensor information or multiple sensor, combine those knowledge to make sense of those data and explain the question like how many people in the room and what it sees, what are the objects. So object recognition, it doesn't come for free. You have to develop a image processing algorithm, computer perception algorithm to come up with the object segmentation, object recognition.
Okay. So the next one which we have is there any internship available for robotics?
Sorry?
Is there any internships available for the available in robotics? If yes, it's paid or unpaid.
Uh, this is a good question. I cannot give the 100% sure answer about this question. We offer a paid internship sometimes, and we offer non-paid internship. It depends on what kind of internship we announce, and we usually announce it via web
Yep.
page and in the robotic worldwide mailing list. But the problem with the internship, especially for those people who are outside UK, EU, is the whole visa issue, which I don't know the details. I think the people in our admission office or marketing people
Okay.
could answer this question much better.
Okay.
But the short answer, yes, in general, we offer internship for summer.
Okay. So the next question which we have: do you organize any summer schools, winter schools program in robotics?
Uh, okay. It At the moment, no. At the moment, I don't think anyone does. But we do not have a regular summer school or organization or winter school or any of this. But occasionally, each of our colleagues, they may have some summer school in a specialized topic, for example, computer vision. Well, but at the moment, no, we don't have any summer school.
Okay. The next one is on which platform we can run robots to learn the route.
In which platform we can run robot to learn? Sorry,
On which platform we can learn robots to learn the route.
the route, like the
Yeah.
path.
Yeah.
Uh, this is a very general question. It's like uh, route planning or path planning. And why topic is that is. is one of the important topics in robotic. And if you go to robotic conferences, 1/3 of the paper is about path planning. And the state of the art approaches is actually is not about learning, is about roadmap based approach or RRT based approach. Is a basically probabilistic path planning, which is very fast. Of course, these are the basic approaches that many people use. In order to enhance this, people use different learning. It depends really what kind of route you want to learn. For example, you want to learn an immediate short plan, motion plan for an autonomous car, it requires a different method rather than to find the sequence of route for the mining example that I showed you earlier. They're totally different. So there is not one single answer to your question. It really depends on the domain, what kind of robot you have. Are you talking about the route in abstract level? So basically, the learning method, a lot of people use at the moment reinforcement learning, but in order to make a reinforcement learning work, so and it basically converge, you have to have a simpler sort of environment. But at the same time, if you have many data, you can use deep reinforcement learning. But again, there is no one fit solution for all problem. It really depends on the application and constraint and the road.
The next question is the further extension of the previous question. How can we taught or teach robots to learn the route?
Is it the same? I would answer exactly the same. This robot, I mean, yeah, if
Okay.
you want me to answer the question, you have to really details the application. So, or point out to the different application I said in that presentation, and then I can explain which in the application, apart from the learning of the polishing, the others is actually not learn. And there was some learning in the time travel time. So I learned with simulation and use this information as a probability distribution in the stochastic Petri net, but it's a combination of learning and reasoning. Again, is not that you can learn everything. Even the most important, not the most important, the most famous application of AI that most people knows about, like Go, is a combination of learning heuristic via deep neural network and the Monte Carlo search. Basically, the search algorithm, very classical AI algorithm on top, and they use learning to explore the search tree. And it's not that everything is learned. You learn a bits of an application, you combine with different reasoning, research, or the other techniques to come up with the solution.
Okay. So now we have one student who is asking how to deploy ML model in robotics.
How to deploy machine learning models in robotics? Again, this is a very general question. It depends on the task, and then there are at the moment. Are you talking about computer vision? Are you talking about motion planning? Are you talking about task planning? So there are different techniques, different machine learning techniques for different tasks. So if what you should do in robotic, you should not think about, okay, I have this model, how I can deploy it. Rather, I have this problem, which solution is best? In computer vision, at the moment, all the successful applications related to deep learning. So if you want to do something with computer vision, I don't know, pose estimation, object recognition, object segmentation, the best current approach is using deep learning. But if you want to do planning, you may want to do different type of reasoning and planning, or use combine it for deep learning or any other type of learning. It really depends what task, what problem you have. And then the answer maybe would use a machine learning techniques. Then you have to ask, okay, which machine learning technique is good for this task? Do I want, this is a regression problem, this is a classification problem, and then, okay, what kind of feature I have? So do I have many data? Do I have little data? So there is a lot of question you have to answer before thinking which machine learning to use and how to use it. And then when I have a model, of course, and then if you answer all these questions, when you have a model, is the easiest thing. So you just use it. So the problem is usually come up with that model is difficult. And and of course the you may want to think about the end result in terms of the knowledge representation that easily would fit or caters to the application you have in your hand.
Okay. Now again we have student. I mean that's the general question. Which course is best to do in MS in UK? I mean that's more generic question.
Which course? You
Yeah.
mean which program or which module?
I mean which course? I mean slash program is best to do in MS in UK. I mean from an engineering perspective.
Okay, again, this is a very general question.
Yeah.
Depends. If you are interested in intelligent robotic, so of course you have to find out uh, a robotic program that is in computer science department. If you're interested in building a robot and less interested in machine learning, planning, and all AI stuff, uh, of course, in a robotic program that is offered in mechanical engineering or is more suitable. It doesn't mean that they don't do AI, but of course we have more focus on knowledge representation, reasoning, artificial intelligence than, and a robotic program is taught in the mechanical engineering department of the university. And both are interesting, but it really important a person, what person really looking for. And and in the advanced robotic module that I'm teaching, I have a student from different background. I have a student from computer science. I have a student from mechatronics. I have a student from mechanics. So uh, they are from different background, and now they come here to basically learn more about intelligent robotic in a sense, rather than how to build a, I don't know, manipulate or to do something. I don't know. So it really depends on the person.
Okay. So a few more questions. Uh, if students wants to pursue the master program in robotics, what's the procedure for that?
Uh, if you want to well, the you have to go to the university webpage, and you have to go to the official process of admission. Uh, sorry, and then provide the necessary grades and the language and all the requirement it needs. So it doesn't come through the department. It's actually the central unit they have to go through, and the requirement is clearly explained uh, in the web page. I don't have him in my mind, and I don't want to say something which is not precise. But if you go to the university admission, and you will see it basically is a uh, having a bachelor degree or equivalent of bachelor degree in computer science, or topic relevant to computer science like mechanic, I don't know, mechatronic and all these things. And also you require uh, a language certificate, which could be of many, it depends, but you have to prove that. I think these are the two main requirements that that are necessary for studying a master in
Can I just
robotic in our department.
a few words more. Can I just add in the NP requirement?
Yeah, definitely, ma'am.
So, students from India, as Professor has mentioned, we do require students to have a computer science background in the bachelor's degree. So we require a 2-1 equivalent, which is, if we compare it with the Indian qualifications, it's a first division or a higher second division from your university in India, which should be a recognized university by the University Grants Commission. And if it has a NAC accreditation, it would be great, um, but it's not compulsory. And as she mentioned, we also ask you for an IELTS score. So for most of these courses, we ask you for an overall 6.5 with no less than 6 in any band. Additionally, you have to provide us with 2 letters of recommendations. These are your referees from your university which you're currently studying. So if you have some work experience, then you can provide 1 academic reference and 1 professional reference. So a minimum of 2 references are required, and you also have to write a statement of purpose so that you can, tell us a little bit about yourself and why you want to do this course and what interests you about it, what motivates you to do this program, what are your future goals and aspirations. So we can provide you with more information about it. You can get in touch with us.
Okay, thank you very much. So here we come to an end of the session. So here I'd like to thank Dr. Mansoori for coming all the way from the university and guiding us, and for the wonderful and the informative session. Again, further, I'd like to thank everyone for participating in the webinar today.
Thank you for having me.
Yeah,
That was a
and
pleasure.
thank you very much. And just to for the student for the participation, uh, just to inform you that tomorrow again we have one more session, and the topic is related to the engineering background only. So do join us for tomorrow as well. So thank you very much and have a great day.
Thank you.
Thank you.